He gave me the instruction. Yeah, what I have an hour. I don't know. I want questions.
Yeah, I think we'll be questions. You want me to warn you 10 minutes before?
Yeah, 10 is good. Most likely I'll go under because it's like I want to talk
10
about
minutes.
Thanks everyone for coming bright and early for the fourth day of this workshop. And it's my great pleasure to introduce Max Raginsky. He's a professor at the University of Illinois in the EC department. And a fun thing about Max is every time people meet him, they always refer to one of the many fields he works in. And it's always a surprise to Max. He's like, oh, you're referring to me as an information theorist, whereas the last thing I did was a machine learning paper. And the reason for that, he's respected across a ton of fields. He's highly respected. People just know about some big results in one field or another one. And I just wanted to reveal a little bit of Max's secret sauce behind this. So, and I'm sure we'll see this on display today. If you ever get to meet Max, you'll find out very quickly that he has a phenomenal ability for reading and recall. So I'm sure we'll see it on display today. We're going to see that he basically read the entire literature on 5 different fields and memorized every detail of every paper and can synthesize them for us, right? That's the topic today, right? That's what you did?
Sure, yeah.
Okay, good.
All right. Thanks a lot, Matus, for the introduction. A less charitable way to spin it is, full professor waxing philosophical because he can't do anything else, but it's okay. There will be philosophy because we can't, if you have emerging generalization settings in the workshop title, and then you pose this question about, what generalization means, and then somebody who's sort of dabbled in philosophy of science and will immediately say, oh, you're asking to solve the problem of induction, which cannot be done. And my goal is to basically explain that, yeah, it can't be done, but it's not too bad. We're okay. The word behavioral here actually has a technical meaning, and I'll get to it almost right away. So I'm an engineer. I'm in the EE department. I'm not interested in building an intelligent super god or whatever. In fact, I'm pretty sure it's not possible. But I'm interested in a problem which basically has a learning flavor, and is device modeling. I collaborated with faculty in my department who do exactly this. The field is called electronic design automation. And a lot of times what happens, you have a brand new device that some company manufactured, and it does amazing things, but it's protected by intellectual property. So you get it. You don't get any information about what's inside. You don't get schematics. What you do get is this device that you can plug into various circuits and measure what it does. And you also get simulation software that the manufacturer provides. It's basically a piece of software that you can use in any standard circuit simulator. And it's encrypted to protect their intellectual property. But you can generate mathematical models of various stimuli, subject the device to those stimuli, the device model in software, and the software will simulate what this device is going to do. And either having the physical device in the lab or having this piece of software allows you to characterize what this device does. And this is a picture from a 1980 paper by a Berkeley faculty, Leon Chua, who really espoused this philosophy without really calling it the behavioral modeling. And the idea is as follows. You want to separate experience, what you actually can measure or simulate, from models. Models are descriptions of that. In the world of device modeling, here's how that works. You characterize the behavior of a device as a collection of all possible current and voltage waveforms you can generate by connecting it to some other circuit, like this, flipping the switch, and then laws of physics, things like Kirchhoff's law of voltage and current, and the internal structure of the device will cause certain relations between the current that you can measure here with an ideal ammeter, and the voltage you can measure here with an ideal voltmeter. And all possible such collections of current and voltage is completely exhaustively described this device. If you're familiar with this notion of extensional description, that's just listing all possible things that a certain, all possible attributes a certain object can take. That is its extensional description. But that's not useful. right? Because you could characterize the device completely this way, but you're not going to use that in your work as an engineer. You want to take that device and you want to make statements about what it's going to do in various other circumstances. You measured it, you simulated it, but you want to use it in some other circuit. Sometimes you might even have a hunch as a good engineer that even though this device was intended for one thing, if you use it in a totally different situation, you suspect it has some other, quote unquote, undocumented properties, and then you make conjectures about that. So for that, you need a model. A model is a mathematical construct which is different from the device itself. It allows us to make prediction about this device in various circumstances of interest without really having to enumerate or measure all the elements in its behavior, because it's impossible. Right. So, and this is a you could look at it and you say this is a machine learning problem. Towards the end of this survey in 1980, the state of the art in 1980 was what it was. There are examples of how various devices first had been sort of postulated theoretically, then manufactured, and then characterized in the lab. And actually, Chua describes two methods. One is model-based, and one is, he calls it black box or model-free. Both are useful. Like I said, I already gave you two descriptions. Model-based is when you take a circuit simulation software, which basically specifies what you would call a computation graph. And in fact, if you want to talk about all this differentiable programming, that's what a typical circuit simulator does. You describe a device by means of differential equations that are supposed to be well posed. So, you're supposed to use smooth, infinitely differentiable functions, so hyperbolic tangents, not ReLUs. Even the model of a diode, even though ideal diode can be described as a very steep ReLU, you can smooth it. And so that's a mathematical description in the form of a bunch of equations. But that encrypted modeling block that a manufacturer provides a black box. And both are valid, both are models. So what do we want from a model? Right? We want well-posedness. And in the context of device modeling, it means that the model should not say anything unphysical. For example, what's a battery? You just plug it into a circuit that provides enough voltage to run the thing. But you can't model a battery as just a voltage source, because if I can take a 9-volt battery and a 6-volt battery and I connect them in parallel, each battery has resistance. This will not lead to anything unphysical. But if I treat the battery as just a voltage source, I connect them in parallel, well, that's going to be an unphysical situation because the voltage has to be the same in this between these two pair of terminals. So that means that well-posedness is important. It should not lead to solutions that blow up in finite time, et cetera, et cetera. It has to have simulation capability. These are all Chua's terms, but simulation capability basically means that I can measure a bunch of sample waveforms, and I can fit a model to that, and it'll have low training error. That's basically what simulation capability means. That it's good inductive bias, at least for the purpose of finding one model in my class that fits the data well. You have to have qualitative similarity. Qualitative is kind of a vague concept, but if you expect a device to be nonlinear and have memory, something like hysteresis, you actually want the model to reflect that. You want predictability, obviously. Again, the reason why you want to acquire a model of this device is you want to use it in various other circumstances. Again, as I said, if you're a creative engineer, you might think of a new use for some old device that has not been used in that setting before. And finally, you want structural stability. That just means that the model should not really depend on fine-tuning of the parameters. If I change the parameters of the model slightly, it should not result in anything super qualitatively different. And so then you can say that from this point of view, a model extracted from a set of measurements should generalize, right, to previously unseen operating conditions if it has good simulation capability and good predictive ability against the background of all these other requirements. And the thing is that if you're looking at this as a machine learning problem, like, no worries. I'll just have a random signal generator that'll generate sufficiently rich set of stimuli. Let's say I decide to have a voltage source. The current will be determined by the device and the interconnection. I select a whole bunch of voltage waveforms randomly from some distribution, and I let my nonlinear regression neural network thing rip, and it comes up with a model. Well, the thing is that any probabilistic assumption about any subsequent use case for the circuit would be highly artificial, because what is that distribution anyway? Is there a distribution? Let's talk about in distribution and out of distribution. We keep hearing these are just convenient fictions that we tell ourselves. In the context of engineering, when I have a device, there is no distribution from which stimuli come from. They really are determined by human purposes. We want to build devices to serve certain functions. Formalizing that with a distribution is just doomed from the start. In fact, I want to remind everybody from this quote by Bruno De Finetti. I'm not a subjective Bayesian by any means, but I think this quote is right. Probability does not exist. It's a fiction. And the reason why he said that is that you can never empirically verify a probabilistic statement. Even something as trivial as a fair coin. I take out a quarter from my pocket and I say, this is a fair coin. And what does that mean? It means that the probability of landing heads or tails is 1/2, but how can you verify it? It could be that I really suck at tossing coins. That's probably true. So in fact, any sequence of tosses that I do might deviate from that 1/2. And that's not really a property of a coin anymore. It's property of the coin plus the tosser, who may or may not be good at it. In fact, Percy Diaconius at Stanford, with colleagues in the physics department, built a machine that really tossed the coins properly, and they showed that there's a slight bias in this device. So you have to model a device. In this device, that the coin will have about 51% chance of landing the same way that it was put into the device. So the point is that probabilities are just convenient fictions, and in the context of something like device modeling, we can't really meaningfully talk about, oh, these stimuli were out of distribution. What does that even mean, right? So instead, I suggest taking something called the behavioral approach, which was developed by Dutch control theorist Jan Willems in the 1980s, but it actually has a rich history in what's called general systems theory, which was this approach of formalizing what we mean by a system in the abstract, and then descending from that to concrete models. So 1970s, a very rich literature. Some names here: Brian Gaines, George Clear, Mihailo Misharovich, George Windeknecht, and Lotfi Zadeh, who I believe was here at Berkeley. So the behavioral approach, basically, this subtitle, "By their fruits you will know them," it says exactly that. It says a given system is exactly its behavior. It's all possible attributes that you could measure on that system. Of course, then you can enter into questions. What does it mean to measure? What do you need? What is meaningful to measure? Yesterday's talk by Sanmi really got into that whole question of metrics. But assuming that you have all these background assumptions, that you specified a set of observables, you're okay with other things like clocks. You trust your clocks. You trust your measuring devices for other attributes. You describe a system virtually, because there's no way to completely measure it, by all possible trajectories that could generate. So that's, like I said, that's called an extensional description. When you specify something by extension, you just list all possible manifestations of that. Or, you say, okay, manifestation 1, manifestation 2, ... use your imagination. But a model is described instead intentionally, meaning that you really you specify a set of necessary and sufficient conditions for a given tentative attribute to be part of the behavior or not. And these are done by means of what's called behavioral equations. And the goal of learning or modeling or system identification, which is determined control, is proceeding from samples of behaviors, that is data, to models. In fact, Willems gives a very nice example again from history of science. When Kepler formulated laws of planetary motion, he described them as ellipses with certain other properties having to do with how the planets move along their elliptical orbits. And that's an extensional description. It really exhaustively tells you which sets of ellipses and motions along them qualify as planetary motions and which do not. And then it took until Newton to actually come up with an intentional description arising from the inverse square law of gravitation. Yes? Yeah.
So the thing you were emphasizing in this slide was the thing in the orange box, that
yes.
This classical notion is exactly a notion of OD generalization.
Yes.
I was wondering if you also had a secondary point, which is that these systems were designed with these 5 desiderata, which were intended to allow for this out-of-domain generalization, whereas in contrast, in contemporary machine learning, we do not have a set of desiderata like this.
I think we we kind of do. There are other, and I'll get to that. There are other sort of what you would call auxiliary theories. Comes from philosophy of science that actually are lurking in the background. We just don't talk about it, but they all came up in various talks. Now, in fact, I'll come back a bit to large language models in this context and flesh that out. Yeah, thanks. Oh, by the way, if you want to ask a question, you can raise your hand. I won't see it because my eyesight is terrible. So just speak up. Anyway, so here's some generalities first. So the basic object is a pair WB, where W is a space of all possible outcomes or measurable attributes. So already comes with some theoretical assumptions. We have agreed that these attributes are the ones that matter, and those other ones don't. And we have a subset of that called the behavior. So that describes the system exhaustively. Like I said, think about all possible current voltage waveforms that a given device can generate for any choice of the excitation network, of course, under various assumptions. Like if I have a pair of speakers, there's going to be some impedance rating. If I crank up the volume too much, I'll blow the speakers. But within the universe of sort of reasonable operating conditions, that's how it's going to be. So models, by contrast, like I said, are behavioral equations. And again, without really getting into the specifics, there are two types of models that Willems specifies. One's called a kernel representation. You basically postulate that there's some function that maps attributes to 0 or 1, and the attributes in the behavior are mapped to 0. Everything else is mapped to 1. In fact, replace 1 with anything else. Like instead, you have 0, and then you have, I don't know, dinosaurs. And so a behavior is characterized by the preimage of 0, and the preimage of dinosaurs is not in the behavior. Right? That's a kernel representation. It's an equation, right? Now you can actually check whether a given W is in it. Oh, and then there's another way, which is equivalent, called the image or latent variable representation. In other words, here I view the filter that tells me what's in the behavior as acting on the outcomes. Here, outcomes are generated. This is kind of a generative representation. There's some mapping G from some space of latent variables. And so for each W that's in the behavior, there's some latent variable that generates it. Here's an example. All like autoregressive models. So here I specifically used an example where my W is a set of, let's say, infinite sequences of quote-unquote tokens from some finite set sigma. And I could specify that maybe you have to kind of restrict. You basically say there's some time t such that before that you have blank tokens. There's some time t prime which is bigger than t such that after that you have blank tokens. You have a finite sequence of non-blank tokens. But the point is that there's going to be some function that allows you to say that the token at time I is a given function of the previous L, the context of length L. And that's a description. That's a behavioral equation, which is an autoregressive form. And so the goal of modeling, the way that Willems and some of the precursors in the 1970s framed it, is to start with some partial glimpse at the behavior and arrive at a description like this, which is exactly what we do in learning. So this is one of the first papers, and it's called From Time Series to Linear Systems. Time series is exactly sequences of observations. Linear system, you claim that there's an equation, let's say linear autoregression, that describes you slide a window of a given length along your sequence, and that imposes a linear relationship between the corresponding variables. And getting from samples of sequences to these coefficients is a problem of system identification, and they're supposed to be data-driven. Data-driven here reminds us that what we have to work with is a partial view of the behavior plus some background assumptions, and they are very important. And what we go to is a model. So these are two papers. If you want to spend the time to get to know this framework, this is a paper I recommend, Models for Dynamics. In fact, if you search for Jan Willems, his website is still operational. All the papers are available for download from his website. So this is modeling, and now let's talk about it in the context of in some kind of linguistic framework that we're used to in machine learning. So there's some behavior out there that describes the system. It's sampled. So we'll get to see some, let's say, finite subset of it, this B data. And the modeling will produce an equation model, right? It'll tell us, yeah, there's some function f hat, and I'm reasonably sure that it models what's going on. So in other words, I come up with a kernel representation of my data. And now we can talk about all the things we like, for example, inductive bias. That's simply the choice of function class from which the behavioral equations are selected. We can even talk about interpolation. What does that mean? It means that this is a finite subset from the behavior, and it's a subset of b hat. So my model recovers the observations. We can talk about approximate interpolation, of course. We can talk about some probabilistic assumptions. But if we want to really get to the core issues, let's talk about this. In fact, Willems uses the term from philosophy of science. He says that if this happens, if my model is such that wi's are covered by this equation, then the model, the observations are unfalsified by the model. And this comes to philosophy of science of Karl Popper, who basically said that the goal of science, what separates science from other intellectual endeavors, is this possibility of falsification. You make a statement, you have a theory predicts some observation, you don't observe it, the theory is quote-unquote falsified. So it was really sneaky attempt to kind of use rules of deduction, in particular something called modus tollens, where you have an implication, A implies B, and then you observe not B, therefore not A. And of course, so Popper wanted to kind of really claim that problem of induction, meaning you can't go from particular observations to general statements and have a universally valid rule for doing that, is immaterial because science doesn't really work inductively. I think he was wrong about that, and many others do. But the point is that it's still a useful term. It means that your model really says, okay, yeah, we interpolate the observations, but we say something else. And then we can talk about model complexity. So for example, we can consider a nested sequence of these model classes. And for each of these classes, I can come up with a model based on the data. And then the idea is that the behaviors are nested. So the nesting is actually nice because you prefer the ones that are lower in this chain of inclusion because you want the model that forbids more things. Right, again, really crude attempts of talking about model complexity and interpolation. And in fact, Willems has this really nice notion of, he calls it most powerful unfalsified model. A model is more powerful if, again, it excludes more trajectories. The more it excludes, the more powerful it is. And the most powerful unfalsified model is the one that corresponds to the smallest index when you interpolate. Because once you hit a model of sufficient complexity that interpolates the data, you don't have to worry about the ones of larger complexity. Again, one can elaborate on this in various ways, but it's interesting that these ideas have been kind of around in the realm of system identification without really thinking much in terms of statistical assumptions. But I like to give examples from machine learning. Here's one. I'd like to thank my friend Alyosha Efros, who's also faculty here. He loves nearest neighbor methods, and I promised to him when I had dinner with him Tuesday night that there'll be a nearest neighbor example, and there it is. So you assume what's called the realizable case. You have a classifier F that separates instances in some space X into two classes, 0, 1. You don't know what that is. You just get a bunch of samples. And so a nearest neighbor classifier is exactly this. You say, OK, I'm going to memorize all of the features in my set, and I'm going to take a new feature, map it to the one that's closest to it in the training set, and just copy its label. And you can see that this obviously is interpolating or unfalsifying model. But that's the most you can say without imposing probabilistic assumptions. If you do impose some probabilistic assumptions, such as that x's come from some distribution, they're sampled independently, then you have beautiful guarantee, for example, something like covariant Hart, that nearest neighbor rule will have expected error, which is at most twice the minimal possible Bayes error. But again, that justifying this probabilistic assumption has to be done. You have to take a risk. Because if you want to have a universal justification, then you have to have some sort of like a meta probability that samples probabilities. But then what is the meta probability sampled from? Well, the meta probability. And then you have this infinite regress that David Hume in the heyday of Scottish Enlightenment warned us about. Here's another example, is interpolating regression. This is where you can have kernels, use the Nadaraya-Watson estimator, and the kernel is singular. There are certain kernels that result in well-behaved regressors, but the kernel is such that if its argument approaches 0, the kernel blows up. And you can show, under suitable assumptions on the kernel, that this will interpolate the data. This will memorize the training data. Basically, if you give it xi, it'll spit out yi, which is, of course, again, the data are unfalsified by the model. And then if you're willing to make assumptions like x, y are sampled from some distribution IID, and this unknown function comes from particular smoothness class, if statisticians' favorite smoothness class, you can basically argue that this, despite quote-unquote overfitting, actually has favorable statistical properties. So, nice paper by Misha, Sasha Raklin, and Sasha Tsibakov in 2018, for example. It's very short and very, very clean about this. So point is, like, we're familiar with all these concepts. I'll give you an example from control. Beautiful result called the fundamental lemma. Everybody calls it fundamental lemma. The authors did not call it. In fact, the paper has no note on persistency of excitation, but it's an awesome result. So to tell you what this result says, I have to give you a bit of background, which also is more advertising for the behavioral approach. Now everybody likes talking about linear systems because, I think we're told that linear systems can replace transformers, right? Linear systems are described by a set of state space equations that are linear in the state and the input, right? But that's an input-output description. That's a model. How would you characterize a linear system behaviorally? And Williams has a very, very simple answer. He says, a system is linear if its behavior is a linear subspace of a vector space. That's it. If I have a trajectory, which is valid, I can scale it up or down by some scalar. That's going to be another valid trajectory. A sum of two trajectories is another valid trajectory. And we say the system is time invariant if the subspace, this behavior is invariant with respect to shifts. So here's an example of specifying a discrete time linear time invariant system. The set of outcomes, set of infinite sequences, let's say with vector valued entries. And this is a kernel representation. It's really cute. Sigma is a shift operator, and I consider its powers. So every time I apply the shift twice or 3 times or whatever, and every time I shift, I multiply the output of that by a matrix. So a linear time invariant system is always something that has this representation. This is a polynomial in sigma with matrix valued coefficients. And the fundamental lemma, without getting into too many technicalities, says the following. If I have a linear time invariant system which is controllable, controllability is basically the property that if I have a given past and I have a given future, I can always find a trajectory in my behavior that connects this past to this future. That's controllability, the behavioral statement. But so you have to make these assumptions. This is part of your inductive bias. System is linear, time invariant, and controllable. Then I can reconstruct the restriction of its behaviors to a given finite length L from a single observation trajectory, which is longer than L, assuming that it satisfies a certain property called persistency of excitation, which has to do with certain matrix ranks being full. And in fact, this gives you a recipe. If you collect such a trajectory of length t, what you do is you form a matrix where each column of that, the first column is just the first L elements of that trajectory, then you shift it, and you keep shifting until you exhaust the trajectory. So basically, the behavior is the column space of this matrix. That's it. And in fact, there's a nice, it definitely has this representer theorem flavor, and the RKHS interpretation was obtained recently, just this year, by Malonchik and Fallwasser. So it really tells us that your data is just a single trajectory that you have designed to have this persistent excitation property. So that's go back to that example of device modeling, measure the the current and voltage waveforms, assuming that the device is actually a circuit that only has resistors, inductors, and capacitors. That's a linear system. It's time invariant, and therefore you can do this sort of a thing. Just collect one observation trajectory. Here's discrete time, so you sample it and reconstruct the entire behavior. So not only do you interpolate, you reconstruct the whole thing, and from that you can extract the state space equations. And of course, this there's a caveat. There's a strong inductive bias. You have to assume linearity and time invariance and controllability, and you actually have to know something else, because this t has to be related to some system invariance that you kind of have to know ahead of time. And so there are certain material conditions for the validity of this inference that's prescribed by the fundamental lemma. And those are, like I said, controllability, linearity, time invariance, that you have to justify provisionally based on your experience as an engineer. Well, course, you do run into the problem of induction, right? Because you can keep rethinking generalization all you want, but at the end, you're going to run into the following issue. So every time we go from data to a model, this is an inductive inference, right? We go from the particular to the general. But the thing is that there is no universal justification for such inferences. And this goes back, again, to David Hume. Here he is depicted with laser eyes staring at us, just warning us about this. Like this, this is the warning to this entire program. You will not be able to solve the problem of induction. So you'll have to be really pragmatic about it. But really, what he said in the 18th century, and it still holds, is that any attempt to justify mathematically an inductive inference schema is either fallacious, because, for example, you could try an attempt using deductive logic, which has stood since Aristotle and will continue standing because it's so dreary and boring, and you just write down the rules of syllogisms and whatever. But induction has always been sort of this villain, and so you can't use deduction to justify induction, right? Because that kind of, you're shifting the goalposts. So that's a fallacy, or it's going to lead to circular reasoning, because you're going to attempt to list previous examples obtained using this same inductive schema and say, look, it's been good, but I mean you're back to where you started. Or, which is the worst part, is this infinite regress. If you make an assumption that allows the schema to go through, then you have to have another induction to justify that assumption. Well, you're going to have a meta-induction to justify that, and you keep going. So for these reasons, and I think it's unassailable, there's just no way to go around any of this. Any inductive inference we make will always, yeah, yes.
This is not a description of what you said. Elsewhere, he said things like, the field which explores what happens in the future from the present is the field of probability theory.
Yes. But that's not the only. Not the only way of doing this, right? And of course,
He didn't exclude, or he didn't totally say the induction is impossible. He even directed one to.
Well, no, he said that what else do we have? What else can we do? I mean, we know that it cannot be justified, because in order to justify, as I said, probabilistic statements are not empirically verifiable. You cannot empirically verify, the statement that the probability of a straight flush in poker is so and so. How are you going to empirically verify that? You can't.
You need to.
I know many of this is.
You don't need to, exactly. You don't need to. That's just cutting the Gordian knot, saying we don't care. There's going to be an infinite regress, but at some point we're going to be satisfied with 2 layers of depth.
And you can also say that linearity is impossible to verify.
Of course it is. It's impossible to verify. Absolutely, yeah.
It's the same kind of problem.
It's the same kind of problem.
Problem with
Exactly. No, I mean, there's no. These are all the same problems. Probabilistic assumptions are flawed in that same way. Assumptions of linearity, you have to take risks. That's the only way. So there was actually an attempt to kind of go around Hume's criticism by Gilbert Harman, who was a philosopher, and Sanjeev Kulkarni, who is a researcher at the intersection of learning and control. They wrote this whole set of lectures called Induction and Statistical Learning Theory, Reliable Reasoning, and basically said the real problem of induction is how do you decide whether a given inductive inference is reliable? And I completely agree with that. Yes, I mean, reliability is pragmatic. Again, there cannot be a mathematical justification for it that's universal. I'll come back to that. But pragmatics is good enough. And in that book, it's a short book, they basically say that theoretical properties of empirical and structural risk minimization can be interpreted as reliability certificates, and they can be perfectly fine. And they also said that inductive bias, which is a choice of hypothesis class, in that book they mostly talk about Vapnik-Chervonenkis classes because they talk about classification, but formalizes this other, what another philosopher, Nelson Goodman, called the new riddle of induction, which was something like this. Suppose you have some objects, emeralds, and you observe them at some time t, and you observe that they're green, but a predicate that you can form about them, you called it grew, so they're green up until observation time t and blue thereafter. How can you know? There's no way to know. So he basically said that the way to exclude this is the predicates we actually work with in our understanding of the world are what he called projectable, which basically means that you exclude such pathological situations because the future should kind of look like the past. It shouldn't really matter when you look at the emerald. And so they had a different example that basically said, suppose I have a bunch of gems and I weigh them, and based on the weight, I try to, that's my feature. because time is weird. Time just flows one way, and that's it. But if I weigh a gem, and based on that feature, I'm asked to infer its color, it's the same type of problem. And they basically said that, well, you wouldn't choose, that's a bad choice of features. Your resulting classifiers will probably overfit. You don't want to do that. But ultimately, they relied on this IID assumption, and so that approach of going around the problem induction fails for two reasons. First of all, you don't use a deductive argument to justify inductive inference universally. And secondly, you cannot verify a probabilistic assumption. Just like I said, you totally cannot verify assumption of linearity or time invariance. That you always have to take risks. So back to device modeling, right? So really, when I do this, everything really comes down to the choice of this excitation network. For example, it could be universal signal generator, like a neural net. I have a neural net with tunable parameters. I'm guaranteed that by tweaking these parameters, I can generate any, let's say, voltage waveform. So sample a bunch of these. That induces a probability measure on paths, which you don't want to deal with. Those are complicated. But you have a finite dimensional probability measure on the parameters of this device. Collect measurements. Let your favorite nonlinear regression thing run, and then there you have it. But we cannot guarantee good coverage. How do we know that this distribution, whatever it is, which now is instrumental because we chose it, covers all possible operating conditions in the future, right? So no universal procedure for completely characterizing device behavior from finitely many measurements. But we have to live with that. That's fine. A better option was a proposal by a philosopher, John Norton, called the material theory of induction. He starts with two slogans. He basically says all induction is local. So there's going to be domain in which inductive inferences can be made, and you're going to be relatively safe there. And there's no universal rules. It's always context dependent. He gives a good example of, here's an inductive inference which is valid. Some samples of the element bismuth melt at 271 degrees centigrade. Therefore, all samples of the element bismuth melt at 271 degrees centigrade. That's an induction. Here's another statement. Some samples of wax melt at 91 degrees centigrade. Therefore, all samples of wax melt at 91 degrees centigrade. Why is this one valid and this one is not? Because we have background facts telling us about chemical elements. So there's all sorts of auxiliary theories that basically tell us that this is what chemical elements are. They're characterized by their, for example, you can characterize a chemical element by things like melting point, boiling point, evaporation, et cetera, et cetera. And because we're dealing with an element, we're pretty safe, supported by this material fact, to make this inference. Whereas wax is not an element, it's a compound. And there are no identical samples of wax. And therefore, you cannot make this inference. So the idea is that any given inductive argument is really warranted not by math. My answer is that you can't solve these problems by more math, because that's impossible. You have to basically defend a whole background of material facts that justify it provisionally and locally. Which is why various companies that use quote unquote AI have to retrain them constantly for this reason. Because we can talk about in and out of distribution, but really all that really means is that, well, our system didn't work. Something has to be fixed.
Like that all elements melt or like at the same temperature is also inductive.
Of course. Yeah, no universal rules of induction. All induction is local. At some point, you just have to take something on faith. But when you take it on faith, you also have to remember there's a network connecting some material facts to a bunch of theoretical statements, and you have to carefully see what happens if you delete one fact from this corpus of belief.
But all the facts are inductive too.
Yeah, they are. They are. So what I'm saying is that if the hope is to have a mathematical theory that justifies induction everywhere, like for example attempts by Solomonov or Chaitin or whatever, that's fiction. And so
Max, I feel like when you were talking about the trilemma, you were kind of epistemologically more in kind of foundational space.
Yeah.
Now you sort of switched into coherentism.
no, okay, so no, I'm in. So if there's a philosopher of science, Hao-Sok Chang, who has this view called foundationism, both foundationalist and coherentist. There's no other way, because it is true that even in any inductive reasoning that scientists use, there's this quote by a philosopher, I forget his name. He basically said that the problem of induction has been a scandal of philosophy, but at the same time has been a blessing of science. You have to do induction, but the point is that because these material facts, at some point, you are going to run into regress, and it could be infinite. But the subsequent steps are so weak, and just so at variance with the established network of facts that's currently available, and the coherence relations between different links in that network. That this again, you always take a risk. That's
I
okay.
guess how much you justify how big of a risk it is. Like somehow that gets justified by how interconnected.
Yeah. Yes. Exactly, and how firmly anchored it is in observational facts. Because like tomorrow, there's no guarantee that tomorrow somebody will not invent a better measuring instrument, and all of a sudden, all these things you took to be facts turn out to be fictions. That's okay. There could still be practical domains in which you can disregard that. For example, relativity versus things that move at regular speeds. That's okay. There's no problem with that. But the point is that so behavioral modeling also rests on background facts that you have to specify. So, for example, in system ID, we know from experience as engineers that in some settings, in signal processing or control, we can, to a good approximation, assume that things are linear and time invariant and possibly passive and whatever, assuming operating conditions are just right. In language modeling, we know from experience, which actually formalized by Shannon in 1952 and by Zelig Harris, who was Chomsky's advisor, and Chomsky decided to completely disregard what his advisor was saying. And Shannon wrote, anyone speaking a language possesses implicitly an enormous knowledge of the statistics of language. And that's basically reliability of quote-unquote next token prediction, because we have that model. You can't extract it because we're pre-trained in some complicated ways based on personal interactions and which teachers we had, which friends, what our parents did, et cetera, et cetera. But the point is that is a fact that it's really hard to dislodge. And so any assumption of this type is fundamentally local and provisional and have to be checked against experience. Again, this is why various companies retrain their models constantly and fine-tune them. So I think I have what? Excellent. So I want to revisit this material theory of induction through another lens that was actually formulated very crisply by a psychologist, Paul Meehl, in this paper in 1990, published in a psychology journal called Appraising and Amending Theories, because that's what we do. This is what we do to our network of facts. We do, minor surgeries on it. This whole Neurath's boat type, argument. We're in this boat, and it's an open sea, and every once in a while we have to kind of, reassemble it. At the same time, taking care that we don't drown, right? But there's no way. There's no way to avoid it. So Meehl formulated this beautiful, very precise meta-theoretical description of how this takes place. So I mentioned a few people from Berkeley. Here's another one, Ben Recht, who's this Substack blog, ArgMin, and he had a whole set of posts on Paul Meehl's lectures on what he called philosophical psychology, which are all available on YouTube. And Ben's posts on this are just full of really cool insights. And this is where I kind of connected the two and two together. So Meehl's view of theory building is like this. It's not this simplistic view. We have a theory. Theory predicts some observations. We try to make this observation. If we don't observe it, it's falsified. That's very simplistic. In fact, there's a whole network of supporting theories, which is represented like this. And this is a logical conjunction of all of these things, which I'll specify. But and this conjunction implies something called a material implication. So all of this, all the theories plus background facts and assumptions imply that if I were to make observational one, that would automatically lead to another observation 02. And there's this little disclaimer, which has probabilities in it, but I think this is more of kind of a vibes-based kind of thing. Basically, you just somehow argue that, well, without the theory, the probability of seeing 02 given 01 would be very small. So meaning everything else held the same. If this theory that you're proposing is not true, then the probability of that, you don't quantify it, but you just argue it would be very small. Typically, the way it's done is by basically saying that my theory predicts this and that and this other thing, and you make the observations, and all of those things pan out, and then the term is the theory is remarkably detailed, as Paul Meehl wrote, and in close accordance with the facts. And another philosopher of science, Wesley Salmon, basically used the term damn strange coincidence, that if all these observations panned out, but your theory weren't true, would not be a damn strange coincidence. This probability quantifies that. What are the pieces here? So there's a core theory. So first I'll list it, and I'll tell you the example, exactly how it fits into this device modeling thing. There's a core theory, which is what you want to establish. It comes with a whole bunch of auxiliary theories that support this theory. Maybe some idealizations, some approximations that you know are wrong, but you make them anyway. There's going to be auxiliary theories about the instruments. So your instruments measure what you say they do. There's going to be something called the ceteris paribus clause, all else being equal, which basically means experimental conditions roughly describe sets of circumstances in which this theory will be applied in the future. And there's particulars about experimental conditions. Did you ground your, you're measuring, did you ground your circuit? Did you, protect, is your humidity filter on? Stuff like that. And finally, so Ben added this clause to it called software validity assumption, because these days, everything is run on software. We talk about AI for science, right? But everything really rests on a bunch of software packages. And if you run something in like one version of PyTorch and then you change the version of PyTorch, all of a sudden everything is just completely different. Well, it's a bit of a problem. And you have to find a way to blame the software rather than everything else. So in the context of device modeling, let's kind of unpack this. The core theory, so here's my setup. The core theory is that there's a class of models that describes what the current and voltage characteristics look like in their relation. There's some function of currents and voltages that's set to 0. Auxiliary theory is some assumption I make. Again, that's I have to assume something like maybe linearity, maybe time invariance, maybe passivity, or circuits have transistors in their subthreshold regime or whatever. Then there's going to be auxiliary theory about instruments. So I assume that when I measure currents and voltages, for all practical purposes, these are ideal devices. I can ignore things like internal resistance, etc. There's a ceteris paribus clause, which is all else being equal. For example, experimental stimuli are similar to typical use cases. So my signal generator here, in fact, the colleagues who make these measurements, their favorite stimuli are piecewise linear functions. So they kind of do bring values in some way. Piecewise linear functions are nice because they're dense in a set of let's say Lebesgue integrable functions. Pretty good. But the point is that you don't know whether the actual experimental stimuli, these piecewise linear waveforms, are good approximators of how that circuit is going to be conceivably used in any setting in the future. You have to make this assumption. And then there are particulars about experimental condition. Like I said, are you actually good at making these measurements? You assume that you are. You assume that you've controlled for temperature and humidity. You calibrated your instruments. You grounded everything properly. You're not wearing a very static-prone woolly sweater or whatever. And finally, there's the software validity assumptions. Which version of PyTorch you use to run the experiment? And then and this is the prediction you make. O1 is, let's suppose I hook this thing up to a voltage generator that produces a given voltage waveform, and I predict that when I look at the current, when I measure the current, my model will be roughly accurate. So the thing about what Paul Meehl called Lakatosian defense is that when this observation does not pan out, you don't just throw out the theory. You actually start going back and retrenching and saying, oh, but maybe the system was not linear. Maybe it wasn't time invariant. Maybe there are nonlinearities. I have to account for that, which basically means I might have to revisit this model and add more terms. And instead of just going full modus tollens on it, following Popper and throwing everything out, you tweak it. You keep over parameterizing more and more and more. We do it all the time, and in fact, it's perfectly justified on these pragmatic grounds, because when you test the theory, you don't just test the theory; you test a whole bunch of other things. So when that's the problem, that when you falsify the conjunction, any one of its clauses could be false, and some of them are sort of more. You feel more comfortable sacrificing them than others, and that's that's the best we can do. So there can't be like a general approach to generalization that's just valid all the time. In fact, Willems kind of makes this point. He basically says, well, if we make probabilistic assumptions, they don't describe reality. You can think about them as more like quality certificates. And the more of them you amass, the better. Again, this is all about the damn strange coincidences. That if the world were IID Gaussian, and you use the Kalman filter in your system identification, everything would be good. So you arrange a situation in simulation where that happens, and everything works. That gives you one certificate of performance. Then you say, okay, maybe the world is not Gaussian, but somehow I'm looking for the best linear estimator, which is unbiased, which is again what the Kalman filter gives you in the absence of Gaussianity. And you actually check, that means that you may have to do a lot of bootstrapping, which is really one of the best inventions in statistics is bootstrap, because that allows you to kind of, instead of assuming there's some cosmic probability, you generate all the probability you need. So the point is that there's always going to be this pragmatic view. You have to keep in mind, and basically here what I wanted to advocate is a behavior of systems, where systems are data and models are just the compressed descriptions, has been around since 1970s. And it really underlies a lot of what we're doing in learning. In machine learning, we're given samples of a behavior, and we just want a nice behavioral equation model of it that's reliable. And here I want to say that understanding generalization really requires rethinking probability. Hello, Ben. He knows what I'm talking about. He's watching. He knows what I'm talking about. And lots of lessons from control and system ID. For example, wouldn't it be cool to have something like the fundamental lemma for machine learning? Like, I do want to argue that, I have a universal function generator. If it's rich enough, it can basically almost cover my entire behavior with some guarantees. And of course, we do need a more nuanced modeling philosophy with clear recognition that all generalizations are local because they're inductions. And there's no universal justification for generalization. You really have to, trust your intuition. You have to look at your previous hit rates. Like if you've been successful in the past, most likely you're going to keep being successful in the future, assuming you know what you're doing and you're ready to sacrifice certain components in order to, make the overall theoretical edifice just, still remain remarkably detailed and in close accordance with the facts. And with that, I close. Thanks.
Thank you for the talk. It's really nice. So one question. I'm still not completely hopeless about proving generalization, and of course that's the reason why I'm in the workshop. So in particular, you mentioned a fallacy of such proofs may be infinite regress. I was thinking there might be a fix to this problem if you could reason about the limiting case and down to the risk when you have increasing number of samples for empirical trials.
Yeah. I mean, right. So this actually gets at another interesting idea in philosophy due to Rudolf Carnap. He distinguishes two types of probability. He calls them probability 2, which is empirical frequencies, things that you can actually measure, and things that you can verify by checking somebody's lab notebook. And probability 1, and Carnap had this logical view of probability. He was saying that probability statements of that type are what's called metalinguistic. They're properties of propositions. You form propositions using Boolean operations, and then you add to that possibly countable operations through Kolmogorov axioms, and you assign numbers to these in a consistent way. But these numbers are properties of statements. They're properties of propositions. They're not properties of actual physical objects out there. So you have to take a bit of a leap when you bridge these two worlds. For example, laws of large numbers are a bridging construct, but you cannot empirically verify it. You have to take something on faith. And one way to do it is, again, bootstrap. You just resample and you see that measurements on one sample agree to some tolerance with measurements on another independent sample, and that gives you a bit more confidence. You can't have so the justification is mathematical, assuming that these limiting constructions hold. But when you say law of large numbers, a uniform law of large numbers, some statement holds with probability 1. That probability is just something that you possibly have to justify maybe with a meta probability, but you can never empirically verify it. Possibly you can boost your confidence by just doing a lot of bootstrap. But there's nothing wrong with proving theorems as long as you understand that the probability is there. Is it probability 2 or is it probability 1? If it's probability 1 in this Carnapian kind of idealized metalinguistic thing, it's never verifiable. But you can have a lot of material facts that are kind of corroborated. So I proved those theorems. That's okay. I'm not saying I'm going to stop doing that.
Thank you.
Yeah.
Max, you made an excellent case on the criticisms on the probabilistic assumptions and on the data distribution and the linearity, I guess, or other structural assumption on the data.
Yeah.
But in terms of making predictions, for the sake of making predictions and be correct, a lot of times we don't necessarily have to make either of these assumptions.
No, we don't.
So how do you put, I think, the theory of online learning, right, in this framework, right?
Yeah, so right. Well, theory of online learning, I think that's actually an interesting case because it does not make probabilistic assumptions, but assumptions are still there. For example, you have to assume something about the adversary. Certain algorithms fall apart when the adversary is adaptive, and that might happen when you have intentional actions somewhere in the system. But if you're reasonably sure that the adversary is non-adaptive, then you have a beautiful guarantee, and that you can actually verify. Like all the stuff that Philippe Daoud talks about, this frequential principle of probability, or Voff's framework, basically using non-probabilistic formulations of martingales. All those things, again, you have to carefully spot where you're talking about probability 1 versus probability 2. But if you're careful about that, and if you go by a mix of empirical observations, especially if you make many of them, and online learning allows you to do that, right? You have a stream of observations. You constantly get either corroborations or falsifications of things. I think it's another way of justifying these things. But again, I mean, this is also going to be provisional because you don't know whether the adversary is really non-oblivious. They're just biding their time. You'll never be able to verify that. So you have to be always aware of the fact that some assumptions in your whole meta-theoretical framework are just unverifiable. But some of them are just more easily sacrificed than others. Because you might detect like somebody's trying to jailbreak your LLM. And so then you assume, okay, this is not just a regular user. This is a malicious user. I have a pretty good confidence that that's happening. Now I have to somehow retrain the model or do something else. So yeah, that's the best I can say on that.
What do you think? I mean, I'll try to summarize what Babnik tried to say, but I might be wrong. You may disagree, but I think that in Babnik's book of statistical learning theory is something like current neural networks would be considered like non-scientific because it's a theory that's so rich that it can interpolate any collection of samples or that appears in practice, so that is unfalsifiable. But he also took this language from Popper, and he was kind of concerned of these families that had high capacity because then it wasn't.
Sure. Yeah. Yes.
So what is the view that maybe from this perspective? What is the answer to Babnik that you would give from this perspective?
Well,
networks?
there is, and it's basically skin in the game type of thing, right? I mean, these days, if you look at, and this actually, Ben has a post about this, all this AI for science. It's okay. We have a bunch of NVIDIA chips and we can make these predictions. Scientists, I think, unless you're like a string theorist and you say, oh, the world is described and you have the equations for the standard model plus, superstring, whatever. Scientists want to make predictions. Whether or not, you use NVIDIA and have billions of parameters, or whether you have something like gas law that has just a couple. I don't think it matters anymore. I think if you go beyond Popper's naive falsificationism and instead look at what Miele is doing, I think all of that is perfectly justified as long as you can actually articulate all of these assumptions and auxiliary theories that go into it. And according to Ben, this is the worst one. Like this is, and as engineers we see examples. For example, Toyota vehicles just accelerating spontaneously because their embedded systems engineers were using recursion in a system that was collecting basically critical messages. You don't use recursion when there's a stack because that'll quickly fill up the stack and it's full. You can no longer receive messages that tell you something's wrong. So that's exactly like that. It doesn't invalidate cars. It invalidates crappy software engineering. So, I think Vapnik was a bit too. I think his Popperian view may be held in the theory was originally developed late 1960s when they could fit just a handful of parameters. Somehow everybody loved that quote from von Neumann about using 3 parameters I can make an element, using 4 I can make him wiggle his trunk or whatever. These days, nobody really takes that seriously. If you have a bunch of GPUs, you're going to do it and make predictions because you're going to fold proteins and cure cancer. I mean, come on. Right.
since you're on the slide, Max, like, so somehow, I mean, you didn't talk about this that much, but I guess the Lakatoshian view is you don't toss out like TC.
That's exact. Yes.
It goes into the
Yes. That's exactly. Yes.
What
Yes. Yes.
is
Yes.
the lesson from this, like for today's sort of machine learning, or what, like, or what's the analog of like the generating research program in that?
Possibly training neural nets on their own AI-generated slop. I mean, just literally, that's because I mean, so the core theory, like, I think transformers are going to stay for a while. That's the core theory. And every time you write a paper saying transformers cannot do X, there'll be a typical review says, oh, but your transformer wasn't big enough. That's a typical Lakatoshian defense, actually. Because if you have $100,000 more, you can train a bigger transformer. Everything's going to be great. Transformers cannot fail; they can only be failed, right? That's an example of that. I mean, whether it's good or bad faith is a different thing, but that's exactly it. Right? So Lakatosh was basically saying, like, look, theories have a core that you have to protect at all costs until you can no longer do it. That's the degenerating research program. But until then, you're going to basically be successively going through all of these and tweaking them. That's okay. That's what happens in practice. And and like I said, this is the best way of formalizing it. You can't prove a bunch of theorems about it because Hume basically just more or less convincingly said that you couldn't do it. But you have to use something like that. How can you live otherwise?
We have time for. I want to make a few technical remarks, about the online learning.
If they're a little bit on the short side.
Okay, yeah, sorry, I'll be fast. So for bandit algorithms, I think you can be regret optimal even within an adaptive adversary. The only problem is that you have to cheat and you measure regret, and regret is a very weak notion of.
Yes, exactly. Yeah, that's shifting the goalpost.
I mean, that's not kind of a real problem. That's just more of a practical problem. You could end-to-end.
But I mean, all of this is a practical problem.
Yeah.
Like, this is a practical problem.
Computer matches whether the assembly code you run matches the operational behavior of the computer, which is more instrumental. The last kind of general question is, what about the Bayesian uncertainty quantification? I mean, that's also a framework for making decisions. And in that case, your primitives are kind of you put pairs on pairs on pairs on pairs, but at some point you decide enough is enough, and those are kind of your primitive assumptions. And then
right.
Again, completely distributional. If you don't like distributional assumptions, you can be Bayesian minimax.
Oh, sure. You can do objective Bayes, whatever. Yeah. So I mean, there is kind of there's a Bayesian version of salvaging all this. The best one I know is by Mary Hesse. She wrote this book called The Structure of Scientific Inference in 1970s, where she argues specifically that the personalistic Definitian savage Ramsey probability is a way of also having something like induction. I mean, you can poke holes in it, but again, I think Norton is right. All of these statements are good, but they're always local and they're not universal. That's okay. If you can, I like Bayesian analysis, but you have to justify every single thing. Like frequentists don't have to justify anything, admissibility, whatever. But Bayesians have to go and explain why they chose this prior. And it's not because Nate Silver said everything is about betting, because it's not. You have to actually say, I talked to a bunch of physicists, and they all hate each other, but they all told me the same thing.
All right, let's thank Max one more time. Be back in